Look at this tiny ceramic cylinder. It's about the size of a peanut, yet it holds the energy equivalent of 150 gallons of oil, or roughly 1,800 pounds of coal. Getting that energy out, however, presents an immediate physics problem. You can't just dig up uranium ore, throw it into a reactor, and expect it to generate power. The uranium you pull out of the ground is mostly the wrong kind. Natural uranium consists almost entirely of a stable isotope called U-238. Only a minuscule fraction, about 0.7%, is U-235. And U-235 is the highly fissile material that readily splits to release energy. The two isotopes are nearly identical, with a mass difference of only 1.27%. To sustain a nuclear reaction for electricity, engineers have to artificially increase that tiny fraction of U-235 up to a concentration of roughly 3 to 5%. Pulling those nearly identical isotopes apart requires moving mountains of Earth, synthesizing highly reactive chemicals, and operating machinery at the absolute limits of material strength. The process starts in places like the Canadian province of Saskatchewan, home to some of the highest-grade uranium ore on the planet. Miners face a severe environmental hazard here. The ore sits beneath a thick layer of water-saturated sandstone. Digging directly into it would instantly flood the mine. To access the rock, engineers drill hundreds of deep holes and pump a calcium chloride brine chilled to -30 degrees Celsius through the ground. This freezes the surrounding earth and groundwater, creating a solid, impenetrable ice wall that holds back the floodwaters. With the water held at bay, the uranium ore is extracted, crushed, and milled into a bright, concentrated powder known as yellowcake. But yellowcake is a solid, and you cannot physically separate isotopes in a solid state. So the powder is moved to a conversion facility where it is dissolved in strong acids to produce uranium hexafluoride, or UF6. UF6 is the only gaseous form of uranium suitable for the next step, but it is highly volatile. If this gas comes into contact with the moisture in normal ambient air, it instantly reacts to form hydrofluoric acid, a highly toxic and corrosive chemical. The entire mining and chemical conversion process exists for a single reason: to turn a stable piece of rock into a dangerous gas so that the U-235 atoms can physically move. This gas is then shipped to enrichment plants, characterized by vast halls filled with thousands of tall, cylindrical machines called centrifuges. Inside a centrifuge rotor spinning at an extreme 50,000 revolutions per minute, physics takes over. The immense centrifugal force pushes the slightly heavier U-238 molecules toward the outer wall, while the lighter U-235 molecules stay closer to the center. A single spin only separates a tiny fraction of the isotopes. To reach the required concentration, the slightly enriched gas from the center of one machine is siphoned off and fed into the next, cascading through thousands of interconnected centrifuges. Commercial nuclear reactors require uranium enriched to about 3 to 5%.
However, if you keep passing that exact same gas through the centrifuge cascade, the concentration of U-235 will eventually reach the 90% threshold required to build a nuclear weapon. The mechanical process to light a city and the process to level one are identical. That thin margin is why uranium enrichment facilities are among the most heavily monitored and restricted locations on Earth. Once the target enrichment is achieved, the UF6 gas is chemically converted back into a solid powder. Under immense pressure, this powder is pressed and baked in high-temperature furnaces to form dense ceramic pellets. These pellets are highly engineered objects. Because of the strict global regulations surrounding nuclear material, every batch creates a distinct physical and chemical profile, a concept known as nuclear forensics. If investigators find illicit nuclear material, they can analyze its precise dimensions, the exact U-235 enrichment level, and the specific trace impurities trapped inside the ceramic. These markers allow them to trace a stray pellet back to its original manufacturing facility. Millions of these traceable pellets are then loaded into long tubes made of zirconium, a metal chosen because it resists corrosion and allows neutrons to pass through easily. These long tubes are bundled together to form a completed fuel assembly. The chaotic, trace amounts of uranium pulled from the freezing Canadian earth have now been refined, concentrated, and locked inside a geometrically perfect, highly regulated power source. These fuel assemblies are finally lowered into the core of a nuclear reactor. Here, stray neutrons strike the concentrated U-235 atoms, causing them to split. This fission releases an immense amount of heat, which boils water into steam that spins the massive turbines generating electricity. Humanity's ability to harness this specific chain reaction traces back to 1942, when a team of scientists, led by Enrico Fermi, achieved the first controlled, self-sustaining nuclear fission. That breakthrough didn't happen in a pristine high-tech facility. It took place in a makeshift laboratory, hidden underneath the bleachers of a rackets court at the University of Chicago. The early atomic age relied on brute force industrial methods, what physicist Niels Bohr famously called turning the whole country into a factory. Today, that brute force has been replaced by microscopic precision, allowing modern reactors to safely manage forces that early scientists could barely contain. But that energy extraction leaves a permanent mark. After several years in the reactor, the fuel assemblies become depleted of useful U-235. This spent fuel is intensely hot and highly radioactive, requiring it to be safely submerged in deep water pools for decades until the radiation finally decays to manageable levels. Every time you flip a light switch powered by nuclear energy, you are activating the final step in a massive, fragile chain. From freezing the ground to spinning toxic gas at thousands of revolutions per minute to burying radioactive waste, it all centers around packing the power of tons of coal into a single, perfectly engineered pellet.